I will begin. So last time I called something we did, I called the technique, quote-unquote, completing the square, all right? So I wanted to talk today a little bit about where that terminology comes from. And so this actually is also a kind of a chance to explore a little bit of math history that we don't usually do in this course, but here it is. So people back in like, I don't know, say 1400s, 1500s, something like that, mathematicians back in those days, when they looked at an equation like this, they would think about it geometrically. So they would think about it something like you could make like a little box, right? And the length of the sides of that box would be x, right? And so then you could have another box, right? And I won't do it to scale or anything, right? But the other box would maybe be, technically it should be 26 times as long, right? But I'm not going to do that, just for the sake of, So this would be 26, and this would be x, right? So you could look at this as this area plus that area equals to, 27 units of area. So this would be, 27, well, not 27, but 27 x squared, I guess, right? Anyway, so you could view this as an area, right? And what they did was they said, okay, well, you could take this here and you could cut it in half, right? So I'll draw it again down here. So you take this and take half of that, right? And then take the other half and like make it vertical. Right, this, right? So you'd have x here, you'd have x here, right? You'd have 13x now, 13x over here, right? And so you'd have, you have almost a square, right? Almost a square. But if you wanted to complete that square, what would you have to do? You'd have to add in this piece right here, right? Which would have been what? Oh, I'm an idiot. It wouldn't have, I've been doing this wrong. I'm so sorry. 26x, I should only have x on one of these spots or the other, like this one. I'm sorry. See, I never would have made it as a medieval mathematician. Put my x's where they don't belong. So that should just be 26. I'm a dummy. So the area of this rectangle would be 26x. The area of this square would be x squared. I take this rectangle, I cut it into two, put one of the halves here, rotate the other, put the other half here. Okay? So what's the area of the square that I've added? It's 13 by 13, right? So I've just, making this square, I have to add, this area of the orange square would have 13 squared, which is 169, right? So you knew that altogether, let me draw some kind of circle-y pictures here. So like altogether, this guy had area 27. Right? What's the area of this one? 27 plus what? Plus the square that we completed, right? This which is plus 169, right? $196. Right? But also, what is this? This is, and like I said, completing the square, right? This is a square now. So what is the length of a side of a square that has area 196? What square has, so this 196, by the way, is 14 squared. So you see that's a 14 by 14 square. right? So if this square, rather this square here really, is 14 by 14, what's x equal to? So x plus 13 apparently is equal to 14, right? Because this is 14 by 14, you know? So x equals 1, right? So when we use the phrase completing the square, it's actually a reference to this historical method that was, well known to medieval mathematicians. Now, so I don't know if you ever heard this or not, but like it used to be that mathematicians would ignore negative solutions to polynomial equations. And if you think about how they thought about these problems, it starts to make sense why they would ignore them, right? Because like x equals -1, what would that mean in terms of this picture? I mean, it wouldn't, that wouldn't be a reasonable thing to think about. The other solution here is, in fact, well, what is the other solution? Let's work it out. So this is just you don't have to remember this, or you can ignore this if you want. It's just I wanted to share it with you because I think it's interesting. I learned of this actually on a YouTube video. The Veritasium, you ever heard of this guy? He's the one that did the video of the Los Angeles reservoir covered by the black balls to reduce the evaporation. You ever seen that? It was in everybody's feed like a year ago, right? So that's that guy. He did this like 20-minute video on, completing the square, but also what comes past this is solving the cubic equation, which is a lot more complicated. But anyway, let's go through this problem. So example 1. So we have x squared plus 26x, and I'm going to rewrite it as -27 equals to 0. Okay, so what was the algorithm for completing the square? Number 1, take half of coefficient of x term, right? And then you put x plus that, whatever this thing is, let's call it Pac-Man. That, and then to be fair, you have to subtract whatever that is, like that. So I wrote out a more careful formula last time, right? But let me just, rather than trying to give you a careful formula, I think I should just work a bunch of examples. So here, what's half of the coefficient? Half of 26 is 13, right? So x plus 13 squared. So when I square out x plus 13 squared, I get x squared plus 26x plus 169. So to be fair, my Pac-Man here is 13. I have to subtract Pac-Man squared, which is 169. I've still got the -127 up there, yeah? Now 169 minus 27 is 196. So what this gives us is x plus 13 quantity squared minus 196, right? But we can take 196 and we can rewrite it as the square root of 196 squared. But the square root of 196 is 14, so what you have is x plus 13 squared minus 14 squared. Oh, but now we have the difference of squares. So we can go back and use difference of squares formula, which was what? A squared minus b squared is a minus b times a plus b. Right? So that's, well, I was looking for that pattern because we can use that to factor. And so this gives us x plus 13 minus 14, x plus 13 plus 14. In other words, we factored it as x minus 1 times x plus 27. So if we're solving this equation, what are the solutions? X equals 1 or x equals minus 27. So the solution that we would not really have been able to visualize is the minus 27 solution. But once you see that that's a solution, like it's pretty obvious why that works when you go back to the original equation and you think about, well, I got like minus 27 squared and then 26 times minus 27. So you got like one more 27 in this than you have in that, which leaves you with 27. It works. Anyway, you can check. But so this is what I refer to as completing the square. Really, the completing the square step is right, just the first step. This is the completing. Completing the square is just this in my book. But this is a useful. Right. Yeah. And but what's more likely to happen is I'm going to say factor this quadratic completely over the reals, if possible. Right. If not, explain why. Let's see here. So, oops. All right. So like, now all of that said, right? This one. Do we need to complete the square here is a good question, right? So suppose you're just tasked with the problem of factoring this, right? You just want to factor it. So what's our first line of defense? The thing we did at the start, right? Like, yeah, 2 parentheses. Right, now, you know the answer here, so it's hard not to know it. But I think if you can imagine not knowing that, you can see, oh, well, 27, you got a 26 here, right? Anytime you see one number, like the numbers are just one different, that means it's like 1 times that, or one's minus, one's negative. So you get minus 26, you know, oh, excuse me, minus 1 and plus 27, right? So that gives you minus and then plus, which is that, you know. So, I mean, point of order, anytime you see that kind of pattern, right, like 8x plus 9, or if I've got x squared plus 7x, or rather, plus 10x, I should have done minus 9, plus 9. Anytime you see like these numbers differing by 1, you got to go, it's probably just this kind of thing, right? So I would say for these, no, I don't need complete the square for these examples, right? Like we should just think through factoring. So you help me out. What's the example 3? Let's see, that gives me minus x plus 9, gives me plus 8. Great. This one? See, I get x plus 9x, 10x. Great, right? So do I need to complete the square for this one? I don't think I do. It's not an appropriate technique, right? But if it's, I don't know, let me just make one up. How about this? You give me, pick any number from 1 to 10. Pick any number from 1 to 10. 10. See, now we're in trouble, right? Because factors of 10 are 1 and 10, 2 and 5, and I can't get 5 back from a sum or difference of those. So this one is a candidate for completing the square. So let's do it. So this one's uglier too because it's got an odd number, which means I have to deal with fraction. So that's x plus 5 over 2 squared. So that's, I take half of that, right? Now I have to subtract the square of what I added here, to be fair. So I have to subtract 25, well, I'll just put, I have to subtract 5 over 2 squared, all right? And I still got the 10 over there. Now I'm gonna rewrite this one more time just to make the fraction stuff easier. So this is minus 25 over 4, and that's 40 over 4, right? 10 is 40 over 4. I wanted to rewrite a 10 as a fourth because then I can add the fractions, right? Need to have them have a common denominator. 40 minus 25 is 15, right? So I get x plus 5 over 2 squared plus 15 over 4. Right, so this shows me, oh, well, so this one, this quadratic is irreducible. Irreducible is just a fancy word for cannot be factored over the reals. Example 6, similar but different. This will do x squared plus 5x. Actually, this time I'm going to do x squared minus 5x minus 10. So how would I complete the square here? Oh, first of all, can I factor? No, I mean, like, factoring's not, it's not happy here because I can't get 5 from factors of 10 added or subtracted, yeah. So x, so I do x minus 5 over 2 squared, and then I have to subtract minus 5 over 2 squared minus 10. Right. So that gives me x minus 5 over 2 squared minus 25 over 4. So like minus 5 squared is just 25. That minus gets eaten up. Anytime we have a square of a negative thing, you can just kind of drop the minus, really. As long as it's inside the square. That minus outside the square remains. That's minus 40 over 4, yeah? So this time, it looks like we're going to have a number here which is negative overall, right? So that's minus 65 over 4, which is not anything nice. So we just, tilt your head, squint, and go, aha, well, that's the square root of 65 over 4 squared, right? Like that, right? And so what we have is x minus 5 halves minus the square root of 65 over 2, x minus 5 halves plus the square root of 65 over 2. So, hooray, we could factor it, right? But it was ugly. So did you see what I did there? Let me elaborate. So square root of 65 over 4 is equal to the square root of 65 divided by the square root of 4. But the square root of 4 is 2. So that's why I wrote the square root of 65 over 2 in my answer up here. I hope that makes sense. And again, cool. As you can see, that we would not be able to do with the guess method, right? Like, guessing method is not good. Like, I can't do it. If you ask me just to guess that, use guess and check method on this, like, I couldn't do it. Unless I had paper, so I could do this behind the scenes and then say, it's this. do another. All right, so how about this one? 2x squared plus 3x minus 10. Factor. Factor it if possible. And so listen, I have been focusing our attention on the quadratic case because I think it's important to pin this down. Your book is much more general in its set of examples here, and we'll soon go to the book examples and start doing all those other examples. I just wanted to carve out a chunk of time in the class to just focus on the quadratic case because ultimately this is really the tricky part. And once you get this, then everything else just kind of, eh. Now this one's annoying because I've got this 2 out front. So the way I deal with this, I take it out, right? So this is 2 times x squared. There's not a 2 and a 3. How do I take it out? Well, I have to say 3 over 2. That's how you take it out. And minus 5. So factor the 2 out. There we go. Now what? Can we factor this with like the guess and check method? I don't think so. I don't think so. So we're going to complete the square again. This is 2 times x. What's a half of 3 halves? Well, it is 3/4, yeah? So 3/4. Yeah, square that guy. And then we have to subtract 3/4 squared. And then subtract 5. So that gives me 2 times x plus 3/4 hello, this is, all right, well, it's not a very good sales pitch. That keeps happening. Like I hit it, and then like it starts with their automatic, hello, this is your extended car warranty, and then it doesn't even finish. It's just like the phone cuts it off mid-sentence, and I don't know what's going on. I don't really care. Okay, so that's 16. Yeah, so we got minus 9 over 16. How many 16ths is, well, 5 times 16 is 80. So minus 80 over 16. So what we got here is 2 times x plus 3/4 squared minus 89 over 16. So what's the square root of 89 over 16? It's just the square root of 89 over 4. I mean, I don't know, that might simplify, but I'm just going to write it like that. And so what we got then is 2 times parentheses x plus 3/4 minus the square root of 89 over 4, x plus 3/4 plus the square root of 89 over 4. There you go, factored. So yes, completing the square compared with the difference of squares concept allows us to factor any quadratic, and also to know when we can't do it. You get it? Okay, let's go on then. Like later in chapter 7, at the end of the course, when we talk about quadratics in their own right, this becomes interesting because if you set this equal to 0, what this is doing is deriving the quadratic formula. So if you look at this, it's really x is equal to minus, so like the quadratic formula was what? I don't know if you remember or not, but minus b plus or minus square root of b squared. So this is from later, yeah? Over 2a. And that's exactly what's happening from completing the square. See, this problem has a equals to 2, b equals to 3, and c equals to minus 10. So this is specifically, minus 3 plus or minus the square root of b squared is 9. And 4ac, that's plus 80, divided by 2 times a, which is 4. You can see those numbers up here, because this is, when you set this equal to 0, minus this or minus that is the 0, which is exactly what the quadratic formula gives you. So another way to say this is, later in the course, at the end of the course, what we've learned is that by completing the square, we don't have to remember the quadratic formula, because in some sense we're deriving the quadratic formula every time we complete the square. The funny thing is, for students, you have a much better chance of numerically getting the correct numbers here than you do if you just shove numbers into this formula and use your calculator, at least for most students I know. Like this formula, it's got a lot of steps. Like you got to do all these things correctly, then take the square root of that, and then take that and add or subtract it from this and divide by that, That said, that calculator will calculate the answer for a quadratic equation. It's built in. Do you know that? So if you go to in mode, I think it is, it's got like equation mode, and you'll find it. Let me just steal your calculator for a second. Ooh, this one's a little bit older. Yeah, it's from my 9th grade. Ooh, maybe this one. Huh. Oh, you need an upgrade, man. Here, let me show you. Oh, forget it. I'll talk about this some other time. Yeah, never mind. It's not in your calculator. See, if I was a high school algebra teacher, I would like your calculator because it cannot do certain things. The one I have, I can just put in the A, B, and C for the quadratic, and it will tell me possible answers. It will tell me the 2 solutions to the quadratic. Oh, it'll do that? Oh, okay. Oh, table. Oh, that table function is handy. That is true. I forget about that. That's something I should actually teach. But no, the FX 115EX, it's like $15, $20 at Walmart, is well worth the money if you're taking a math class. I used to tell people you could, you can get it at Walmart for $12, or you could go to Radio Shack and buy it for $25. So, but then Radio Shack went out of business for some reason. So I don't know. Go figure. Do you know what Radio Shack? Have you ever heard of Radio Shack? Okay. Yeah. I used to love going to Radio Shack when I was a teenager. It was like one of my favorite things. Poke around in there. See what they got. Okay, so let's just work a bunch of problems here. So I'll try to work some ones that are different than what we've already done. So here's one. 32y plus 4y squared minus y cubed. So here, this is it. What example was I on? Is it 8? Example 8. All right. So technically, this is from your section 4.4, I guess. So it's the section 4.4 problem. So we're supposed to factor this here trinomial. I'll let you think about that one. I'm going to write down another one, so I can put this book down. 56x plus x squared minus x cubed. All right. Example 10. P squared minus 5pq minus 24q squared. This one's actually really quite different. Example 11. 8 minus 7 t to the 15th power. Well, whoop-dee. Minus t to the 30th. Wow. Well, fancy pants. Look at that one. Example 12. We will do, where was it? X to the 6th minus x cubed minus 42. And so all of these examples, we're going to be content to just factor it. I will not put on us the more serious task of completely factoring it, okay? Then we have x to the 8th minus 7x to the 4th plus 10. So here's a selection of example of section 4.4 problems. Okay, so let's start with this one. So what would you do? What would you do here? You'd rewrite it. What would you do? You put the y cubed first. Or how about this? We could factor y out, right? See, there's a y here, and here, and here, right? So we could factor y out. That would give us 32 plus 4y minus y squared. And then I'll tell you what, I'll factor a minus out of that. So I've got minus y times y squared minus 4y minus 32. I guess maybe you have that. See, it's funny. Sometimes they completely factor in this. Sometimes they don't. They've actually decided to go further and factor this thing. See, this is. So I got my minus y, right? And I can put a y here and a y here. 32 is what? 32 is 4 times 8, right? So I want a minus 4. So I should put the minus on the bigger number. Minus 8 plus 4. I think that'll work because minus 8 times 4 is minus 32. Minus 8y plus 4y gives me minus 4y. So there you go. Now, I just got done talking about how we weren't going to completely factor. It looks like I completely factored it. My bad. But that is what the book has as its answer to this one, for what it's worth. I would just say the book is sometimes inconsistent about whether or not it decides to completely factor, you know? Like, let's see here. This one, I'll factor a minus x out. How about that? Minus x. And this one gives me x squared. This one gives me minus x. And that one gives me minus 56. I did something kind of sneaky there. Do you understand what I did? Like, by pulling a minus x out, that means that this, so to get back minus x cubed, I have these two, right? But this times whatever I put there has to give me x squared, which forces me to put a minus x rather than plus. And I have to get 56x, so I'm forced to put a minus on this as well. The ultimate judge of whether or not we did it right is when we multiply this out, do we get back where we started? And we do. Can you factor? I think we could factor this, actually. So what did you get? See, oh. Yep. 56 is, what is it? 1 times 56. It's 2 times 28. It's 8 and 7. Ooh, those differ by 1. I like that. And we want the bigger one to win, right? Because we've got a minus x, so we should do minus 8 plus 7, right? And then we get minus 8x plus 7. There we go. Yep. Answered. It is. So yeah, here we got to do something like P, and then we need to put things here that give you a 24pq squared as their answer, right? So like, I know it's a little bit ugly, so we could do things like, so it could be something like 3q and 8q, right, with one of them being negative. Or you could do like 2q and 12q. Or you could do like 6q and 4q. Those are different ways we could get back 24q squared, right? I don't know if any of those are helpful, though. Is the difference of any of those equal to 5? 6 minus 4 is 1. 12 minus 2 is 10. 8 and 3. Which one do we want to make the plus? Which one do we want to make the minus? All right, there we go. So minus 8q plus 3q. So same principles that we've been going by. Just annoyingly, there's this q we don't know, you know. So, but there it is. By the way, you can still complete the square for something like this. It's just when you complete the square, you have to deal with the q. But the same steps would still go through. I could show you if you want. If you can do it this way, then do it this way. How about this one? Well, I'm going to start by, I'm going to pull a minus out because I can't stand having a minus on the leading term. So minus t to the 30th plus 7 t to the 15th minus 8, yeah? So the key here is to look at it and go, okay, so if I let y equal t to the 15th, right? Then what's y squared equal to? It's t to the 30th, right? So what we're really looking at here is y squared plus 7y minus 8. Now all of a sudden it's not so scary, right? Because it said y plus 8 minus 1. Now, of course, we don't want, our answer shouldn't be in terms of y, it should be in terms of t. So then we go back and put the thing, so that's minus t to the 15th plus 8 times t to the 15th minus 1. And there you go. They don't expect you to go further. I will resist the urge to say about how to go further. It's done. Example 12. Same idea, this one. But here we let y equals to x cubed. See, this would be y squared, and then this would be y. Right? If that's, so we have, you know, or I could just write it this way too. This is like, really think about it, x cubed as the, you know, that's the idea here. So 42 is 1 times 21. It's what? Oh, excuse me, 2 times 21. 6 and 7, that sounds good. Because those differ by 1. Do we want the 6 or the 7 to have the negative? Mm-hmm. There you go. Not so bad, is it? And so here, in a similar vein, we think about an x to the 4th substitution, basically. So you want like x to the 4th for this one, because we got x to the 8th. Now this trick only works, right, if you don't have other powers of x, right? If there was an x cubed in here, or an x squared, or even an x next to the 10, no help. But this pattern, we can do that. So 10 is what? 1 times 10. Oh, 5 and 2. Both minuses, right? And so I think that is actually the answer the book wants here. But I would point out that we can do better. Probably the book answer. We can do better. This is x squared minus the square root of 2. X squared plus the square root of 2. X squared minus the square root of 5. X squared plus the square root of 5. These guys are done. They're already sum of squares. Finito, these guys. The other ones, again, difference of squares. So as hideous as this is, x minus the square root of the square root of 2. You don't like that, plus the square root of the square root of 2. X minus the square root of the square root of 5. X plus the square root of the square root of 5 times x squared plus the square root of 2. X squared plus the square root of 5. There you go. It don't look right. What do you mean don't look right? How would that be an answer? I don't know. Well, I mean, it's an eighth order thing, so we don't look at eighth order things that much. But it makes sense because this is 1, 1, 1, 1, so there's 4 degrees here. This is a second order, so you got 1 plus 1 plus 1 plus 1 plus 2 plus 2, which is 8. So it all works together. For what it's worth, this shows you that if you were solving the equation x to the 8th minus 7x to the 4th plus 10 equals to 0, it has 4 solutions. And the 4 solutions are x is equal to plus or minus, by the way, the square root of the square root of 2, what is that? Square root of the square root of 2, what is that? That's 2 to the 1/2 to the 1/2. In other words, it's 2 to the 1/4. So you could call this the 4th root of 2. That's what that's called. So it's plus or minus the 4th root of 2, or x is equal to plus or minus the 4th root of 5. Them's your solutions. Real solutions. There's also 4 complex solutions that come in conjugate pairs, but we're not allowed to know about that in this course. So there we go. Yep. But we're primarily interested in factoring. Okay, so there's 2 problems, factoring and solving. These are different problems. The answer for a factoring problem, as we've done in almost every example today, has been an expression. We start with an expression, we end with an expression, right? And so that's factoring. Every factoring problem is related to a corresponding equation, but they're not the same. We must separate these ideas in our mind. So anyway, I do believe that's it for today. Have a good weekend.